Hello there and welcome to this video. If you're here expecting to see a video on 6th term examination papers, then you're in the right place. If you're expecting to see cute kittens, then unfortunately you're in the wrong place. Because in this video we're going to be taking a look at a problem that I've taken from a past paper, a past 6th term examination paper, and we're going to take a look at the problem solving process, what that looks like when it comes to trying to find a solution to a non-routine problem in mathematics. So just so that we all know what a step paper is, if you've never heard of one before, here in the UK, if you're doing A-level maths or A-level further maths, and particularly if you're applying to university to do mathematics, undergraduate mathematics, and almost certainly if you're applying to a higher ranking university, as part of your admissions process and your admissions requirements to enter that university and to do that course at that university, you may well be asked to sit a step paper, a 6th term examination paper, and to achieve a particular grade on one or the other, or possibly both of the step papers, because there's two possible step papers that you can take. One concentrates on kind of the normal A-level maths content, the other concentrates a bit more on the further maths side of things. So to do a step paper, really you need to have a kind of a very high level of interest in mathematics, and you need to have kind of a deeper knowledge and understanding, much more thorough understanding of the kinds of concepts and ideas that you encounter on a typical A-level maths or further maths course. So strictly speaking, you don't necessarily need to know anything really beyond the specification material for maths and further maths to do a step paper, although in my opinion it would be very unwise to go into a step paper, to sit a step paper without really having any real depth of understanding of the concepts that you come across on your A-level maths course or further maths. So on a typical step paper, the problems that you encounter are going to be of a very different style to what you will encounter on your normal A-level maths and further maths exam papers. The problems will be, you'll be guided much less, and you will really have to have a much more thorough understanding of the kinds of techniques that you come across, differentiation, integration, amongst other things. And you'll also have to have very, very strong problem solving skills to successfully sit a step paper. But it's all good, because if you're applying to do mathematics at university, then all of this is something that you're interested in anyway, right? Problem solving skills, good stuff. We love solving mathematics problems. We love learning about mathematics and developing our knowledge and understanding of the concepts that we encounter in mathematics. So we're going all the way back here to 1990, so 35 years ago. It's 2025 now, 35 years ago, 1990, step 2. I'm going to leave a link in the description to this video so you can download the paper, the past paper, for yourself, so you can see the question, because I'm not going to be writing it all up on the board here. And it's question 8 that we're going to be looking at. So understand that yes, the specifications for A-level mathematics and further mathematics has changed over the years. Some of the things that you would have been expected to know as part of your A-level maths and further maths back in 1990 is not necessarily applicable now, and vice versa. But again, as people who are applying to do mathematics at university, who have a very high interest in mathematics, this doesn't bother us. We want to learn about mathematics at every opportunity, right? So that's what we're here for. So, okay. I've got my computer just below the camera here, so if it looks like I keep looking down here, that's because I am, because that's where the question is. I'm going to write the main details up on the board, but I'm going to be reading things out. But again, I'll leave a link in the description. You can download the past paper for yourself. So we're looking at differential equations here, integration. We're going to be using some integration by parts. The whole point of this video is not just to give you a kind of rundown of the solution, a walkthrough of the solution. It's really to illustrate to you, to articulate to you what the problem solving process looked like for me personally as I went about solving this problem. Okay, a mathematical problem often requires flexibility when it comes to thinking about things, looking at things from different perspectives, trying things out. Sometimes things will work, sometimes they won't work, and it's not getting disappointed when things, not getting too disappointed or too disheartened when things don't work, just moving on to something else, being prepared to try other things out. So this is not going to be me just giving a simple model solution to this problem. There's mark schemes that will do that for you. There's other videos where you can get model solutions to problems. What I'm interested in really is the ideas that I had when it came to trying to find a solution to this problem. What motivated those ideas? How did I come about those ideas? And is there anything there that you can possibly learn from? Okay, so it's messy. There are some things that I tried to do initially that didn't work. And I include these in the video because they are parts of the problem solving process. I don't want to give the impression that everything just came to me like that, because it didn't. This was a difficult problem, as is usually the case with step problems. And I had to think about it very hard, just like anybody else would have to. Okay. So, and I want to articulate that process and really give an idea of some of the messiness that's involved and some of the difficulties that I encountered as I was trying to solve this problem. Okay, so let's get on with things anyway. So it's question number 8 from step 2, 1990. The functions x and y are related as such. So x of t is equal to the integral from 0 to t of y of u du. Okay. So that x primed of t is equal to y of t. Okay, and we need to show that the integral from 0 to 1 of x of t, y of t dt is equal to half of x of 1 squared. Okay, so just while I have a sip of coffee, if you want to read through the information and make sure that you understand the information as best you can, which I'm sure you do. Okay, so how are we going to show this? There's no indication given, and this is very typical of a step paper, whether it's from 1990 or whether it's from 2024, last year, at the time of making this video. It doesn't make any difference. You will just be told to show this or show that or prove this or prove that, and you won't be really given much indication about how to do that. Okay, so fortunately, sometimes you will hit on the right kind of idea very quickly. Other times you won't. This was one of the cases where fortunately I hit on the right idea pretty quickly. What I noticed here is that I've kind of got a product of functions. Okay, so if I want to show that this is equal to this, then I can, in theory, I guess, either go from here to here or from here to here. Well, it seems easier to me, in my opinion, to start with the left-hand side here. And because you've got the product, this kind of screams integration by parts to a certain extent. So let's go for it. Let's try integration by parts. So if we set u equal to x of t and dv by dt equal to y of t, then we get u, or du by dt, is equal to x primed. By the way, sometimes I'll use the derivative notation like this, sometimes I'll use the primed. Just depends how I feel as I write things out. So du by dt is going to be x prime of t, which is also equal to y of t, interestingly. And v is going to be equal to the integral from 0 to t of y of u du. Okay, so you may ask, why have I written the integral like this? Why haven't I got the integral of y of t dt here? And the answer to that is it doesn't make any difference whether I've got t here. I would have to use a different symbol here, really. If I was going to write it out as the integral of y of t dt, I'd have to use a different symbol here, maybe an uppercase T or something like that. This would be fine. I'm doing it really just so that it matches what I've got up here. The variable I use here is a dummy variable. It's not a real variable as such. So whether I replace if I replace this u here with t and replace the u here with t, I still get exactly the same expression. It doesn't make any difference. Okay, so this then is, so I'll just call this I, just because I'm a bit lazy and I can't be bothered writing it out over and over. I is going to be equal to u times v, which is x of t, times, what's this? This is also x of t. So it's going to be x of t squared between the limits 0 and 1 minus the integral from 0 to 1 of, so we've got u times dv by dt here, so it's going to be v times du by dt in here. So that's going to be y of t times, this is just x of t, right? X of t dt. But this is just I. So in other words, if I add I to both sides of this, I get 2i is equal to, plug the limits in here, I get x of 1 squared minus x of 0 squared. Okay, but we need to show that this integral I is equal to a half. Well, we've got the half of just x1 squared, not x1 squared minus x0 squared. But here I've got to look at the properties of integrals. I've got to understand the properties of integrals. Because if I look up at this, x of t is the integral from 0 to t of y of u du. So that means that x of 0 is going to be equal to, and this looks quite unusual to me, the integral from 0 to 0 of y of u du. Well, this is 0. Okay. With an integral, if the limits are equal, the upper limit and the lower limit are equal, the integral is always equal to 0. So in other words, x of 0 here is just equal to 0. So I get 2i is equal to x1 squared, and therefore I is just going to be a half x1 squared. Dead easy, right? So far, so good. So, really make sure that when it comes to trying to solve problems on step papers that you really have a good, thorough understanding of the concepts that you're using. So when it comes to things like integration, there are certain properties that it would be really useful for you to have a deeper understanding of. So one is this property, but you've also got what called the linearity properties. So just before we move on to the next part of this, it's not going to help us, these linearity properties are not going to help us too much here, but well, they might come in useful actually. But I just want to mention them because they are something that often gets overlooked. So I'm going to get rid of this because we're done with this now. But for those of you that don't know what I mean by linearity properties, and I'm just going to change my pen, it's running out a little bit. Linearity properties are things like this. So if you've got the integral from 0, actually no, it doesn't even need to be from 0, it should just be from a to b. The integral from a to b of alpha times f of x plus beta times g of x dx. This is equal to alpha times the integral from a to b of f of x plus beta times the integral from a to b of g of x dx, where we understand alpha and beta as being suitable constants or scalars. We might even take them as real numbers at this point, but they could be complex numbers because you can integrate over complex variables and things like that. But to keep things simple, we'll keep them as real numbers for now. And we've also got additive properties, so the integral from a to b of f plus the integral from b to c of f is equal to the integral from a to c of f. So the upper limit here is the same as the lower limit here, and it's the same function that we're integrating. So these are just some of the properties that you might find are becoming really useful when it comes to dealing with integration on step papers. This is stuff that, by the way, you do encounter this on in your maths course. And I think maybe even in the formula book for A-level maths, these kind of things are stated, but they often get overlooked because there's not really much emphasis placed on these with the normal A-level maths and further maths, maybe a bit more at further maths, but once you get onto step, you really do have to have a better understanding of things like this. I'm not saying that this will definitely come up on your step paper, but it's something to really bear in mind. And there's all sorts of other things. Okay, so let's get rid of that. So we're on to the next part now. Let's have a look. So in addition, it is given that y of t satisfies this differential equation. So we've got y double primed plus y squared minus 1 y primed plus y is equal to 0. And this is denoted by star or asterisk, whatever you prefer, with the conditions that y of 0 is equal to y of 1 and y primed of 0 is equal to y primed of 1, very important. And then it says by integrating star, prove that x of 1 is equal to 0. Okay, a fairly innocuous looking problem, I guess. Prove that x of 1 is equal to 0. So this took me a while to figure out exactly how I was going to do it, because this is a second order. Sometimes you can know a bit more. When you know a bit more about something, that can actually put a block up in a way, because it can send your mind scattering all over the place. So what I saw here was a non-linear second order differential equation, which scare me. Okay, non-linear second order differential equations, not a good thing generally speaking. Okay, linear second order differential equations, if you're doing further maths, these will be a doddle, right? So with constant coefficients, they're easy. There's no difficulties involved with those, but this is a much more complicated thing. And generally speaking, with second order differential equations, you have a lot of difficulty solving them just by integrating. Okay, so this is, as I was reading this, so it says by integrating star, prove this. I was thinking, how do you integrate this? How do you solve it? Because there was something that I was kind of overlooking. Okay, the fact that we've been given this. Okay, without this, it wouldn't necessarily be possible to just integrate this to arrive at this result, but it is literally use the hint that you've been given. Okay, and sometimes you've just got to have the balls to go ahead and just do what you've been told to do. If you've been given a hint, use it. Okay, easy for me to say, and I'm guilty of not taking the hint straight away here it did take me a few minutes, probably about 10 minutes to actually pluck up the courage to just integrate this thing. But go ahead and do it, okay? And what we get is the following. So we get the integral from 0 to 1 of y primed plus y squared. And we've got to bear in mind that these y's and y primes, they're all functions of t. So we're integrating with respect to t here. And this is going to be equal to 0. Integrate the 0 function. Remember, we're integrating each side of this with respect to t. But the integral of 0 from 0 to 1 of dt is just going to be equal to 0, okay? So I haven't just integrated one side with respect to t, I have integrated both sides with respect to t. And now we can use one of the linearity properties that I was talking about, okay? So we can kind of split this down, and we can write it as the integral from 0 to 1 of y primed dt plus the integral from 0 to 1 of y squared minus 1 y primed dt plus the integral from 0 to 1 of y dt is equal to 0. Okay, so I may need to refer to my notes, by the way, when as I'm kind of going through this. Okay. So what did I do next? I've forgotten what I did. Aha. Okay. So yeah, of course, this is just x of 1. And we're wanting to show that x of 1 is equal to 0. So that's where our x of 1 is going to come from. This thing here, okay, this just integrates to y primed of t between the limits of 0 and 1. Okay, so you integrate the second derivative. This is comparable if you wanted to integrate, for example, d2y by dx squared with respect to x. What would you get? You'd get the integral of just dy by dx. Sorry, no, you wouldn't get the integral of dy by, you'd just get dy by dx. Remember that d2y by dx squared is just the derivative of the first derivative. Okay. Yeah, okay, if it's a indefinite integral, then you'll have the constant of integration. But if you've got limits here, then you won't get the constant of integration. You'll just evaluate this derivative at each of these limits. So dy by dx when x is equal to a minus dy by dx when x is equal to b. Okay, annoyingly, there's a fly in this room somewhere, or a wasp or something. Okay, so this is just going to be equal to y primed of 1 minus y primed of 0. But we're told that y primed of 1 is equal to y primed of 0, so therefore this is going to be equal to 0. Okay, so in other words, this part of the integral is going to be equal to 0. So all we've got, so we can kind of cross that out. All we're interested in then is this part of the integral. Okay, so this takes a little bit of, maybe a little bit more work to deal with. Maybe not actually. Actually, no, it's the next part that I'm thinking of. This is relatively straightforward. So this is almost like using integration by substitution, kind of backwards, I guess. So imagine if we had y squared minus 1 dy. If we used integration by substitution, then what would we do? We'd make our substitution. So y equals some function of t, y of t, dy by dt is going to be y primed of t. So we'd replace the dy with y primed t dt. Okay, so this is going to be equal to the integral of y squared minus 1 y primed dt. Okay, don't forget the limits as well. So the limits here are 0 and 1. The limits here would be y of 0 and y of 1. That's important. So as we can see then, this is like integration by substitution, just kind of going backwards in a way. I guess. We're starting with this and we're going back to this thing here. So this is just equal to this. This is a nice easy integral to do. It's going to be a third y cubed minus y between the limits of y0 and y1, which we're going to find is going to be equal to a third of y1 cubed minus y0 cubed. So I'm jumping ahead a little bit here. Minus y1 minus y0. Okay. But again, we've got these conditions: y0 equals y1. That's going to be equal to 0. That's going to be equal to 0. The whole thing is going to be equal to 0. What do we get? x1 equals 0. Easy peasy, right? Well, so far, because we've got a bit more work coming up, a lot more work. Okay, so let's have a look at the next part. Right, so this is where the fun begins. So let's have a look. So you've got to be quite confident with dealing with differential equations, doing integration by parts. You've got to be able to stay organized. That's one of the key things here at this stage, because it took me a couple of attempts to get through this, and it was really because I wasn't really staying organized. Okay, so we've still got the same differential equation. We've still got all of this nonsense up here, and next we're told by multiplying star by x of t and integrating by parts, so we're given a bit more guidance here. Prove the relation. So we need to prove that the integral from 0 to 1 of y of t squared is equal to a third the integral from 0 to 1 of y of t to the power of 4 dt. Okay, so let's do what we're told. So just to clarify, the differential equation that we've got is y primed plus y squared minus 1 y primed plus y is equal to 0. We're told to multiply through by x of t. Okay, so that's going to give us x y primed plus x y squared minus 1 y primed plus xy is equal to 0. Of course, x times 0 is just going to be equal to 0. We're told to integrate by parts, okay, but we've got to figure out how that's going to be effected, right? How exactly are we going to use integration by parts? Because we're just told, we're given a bit of a clue that that's kind of something that we're going to need to do, but it's up to us as the problem solver to figure out what that means, how that clue is exactly going to be used. Okay, so, well, we could start by actually integrating the whole thing similarly to what we did in the previous part. So the integral of xy double prime, and I'm going to split it up from the outset. So xy squared minus 1 y primed dt plus the integral of xy dt, and that must be, again, I am integrating each side of this with respect to t, but that's still going to be 0. So we already know what this is. From the very first part, we figured out that, let me put the limits in, 0 to 1. This integral was a half x of 1 squared, but we figured out that x of 1 is equal to 0. This is equal to 0. Okay, so we can just get rid of that straight away. So we're going to have to do bit by bit. We're going to have to deal with this bit, then we're going to have to deal with this bit. Okay, and there might be quicker ways of doing it, I don't know, but sometimes you just got to get on with it, right? You might have several ideas, you might just have one idea. If you've only got one idea about how you're going to do something, you've got a few options at that point. You can either just kind of get on with it. Just whatever your idea is, just go along with it. You can look for a better idea. If you think that there is a better idea and that it's going to be quicker for you to find an alternative idea than to go along with your current idea, then do that. But you may risk not finding another idea, wasting time and so on and so forth. Or you can whinge about your first idea. Whinge about how long it's going to take for you to do it. Okay, so they're three of the main options that you've got available to you. The third option is, in my opinion, really a no-no. It's not going to help you. The other two, you've got to decide which one you go for. If you've only got one idea, that doesn't mean that there isn't another idea out there that you can go for. It just means that you could end up spending a lot of time trying to chasing another idea that's not going to come to you in time, or it's not going to come to you in a reasonable amount of time. Okay, so this integral here, integration by parts, right? Whenever you've got products of functions that you're wanting to integrate, it's not a guarantee that it's going to work, but integration by parts is often something that you might want to try. It's not a guarantee. It's not like the product rule for differentiation, where if you've got a product of functions, you need to differentiate it, you use the product rule and you get the derivative. It doesn't quite work in the same way when it comes to integration, but it does work quite a lot of the time, particularly at A level. Okay, so let's go for it. So u equals, what do I want to differentiate? What do I want to integrate? Well, I don't want to differentiate y double primed, because then I'll get y triple primed. So I really want to be differentiating the x here, I guess. So dv by dt is going to be y prime primed. Du by dt, and remember, I am differentiating here with respect to t. Du by dt is going to be x primed t, which is, of course, equal to y of t. And what's this going to be? This is going to be v equals y primed. So sometimes I write the t, sometimes I don't. Depends how I feel. So this integral is going to be equal to u times v, x, y primed, between the limits of 0 and 1, minus the integral from 0 to 1 of v times du by dt. So that's going to be y times y primed dt. So this is just going to be 0, because I'm going to get x of 1. Remember, these limits are t, limits in t. So I'm going to get x of 1, y primed of 1, minus x of 0, y primed of 0 for this bit here, which is just going to be equal to 0. So you can cancel those, minus this integral. And again, thinking about this as kind of integration by substitution, but maybe backwards or something like that. The limits here are going to become y of 0, y of 1, y dy. Okay, well, that's nice and easy now. Okay, so this is just going to be minus the integral, the integral of y dy is just half y squared between y of 0 and y of 1. And notice that I do need to change the limits as well, the limits of integration, because I've changed the variable I'm integrating with respect to. And this is just going to be equal to 0. Okay, it's just going to be equal to 0. So we can get rid of that, and all we're left with now is just this bit here. And take your time with this. So much so that I've got time for a coffee. Don't rush things. Very important. Okay, so we can get rid of that. We know that that's equal to 0. And by the way, this solution that I'm presenting to you here is not a mark scheme solution. I don't know what the mark scheme says. I don't even know if there is a mark scheme for this. This is my solution. That's the whole point of these videos, is that I present my solution, which may differ from any mark scheme or model solutions that are available to you. Okay, so let's have a look at this bit then. So we've got the integral, and I'm going to split this up. I'm going to write it as xy squared minus x times y primed, which is equal to the integral from 0 to 1 of x y squared y primed dt minus the integral from 0 to 1 of xy or xy primed even. Okay, yeah, that's what I'm going to do. So what I would like to do here is kind of what I did previously when I had the integral from of y primed dt, change this to just an integral with dy. I can't do that here, unfortunately, because I've got the x in the way. Okay, that causes a bit of an issue for me. So I've got to do things. I've got to be a bit more long-winded about things, I guess. So now we're going to deal with this integral here. And if this solution, by the way, is taking a bit too long for you, that's the way that it is. It's unfortunate. So we're looking at the integral from 0 to 1 of xy squared y primed dt. And okay, so u is equal to, what shall I make it equal to? Xy squared. I just want to make sure. I'm going to refer to my notes because I don't want to get this wrong at this stage. Yeah. And dv by dt is equal to y primed. That means that v is going to be equal to y, and du by dt, I've got to use product rule, is going to be y squared x primed plus, I'm going to need to give myself a bit more space here. It's going to be y squared times x primed plus x times 2xy y primed. Okay, so I've used the product rule here. And remember, we're differentiating with respect to t. So just to clarify, this is y squared x primed plus 2xy times y primed, which in turn is equal to, because I know that x primed is y, this is going to be y cubed plus 2xy y primed. Okay, good stuff. So this is going to be equal to u times v, which is going to be xy cubed between 0 and 1, minus the integral of v times du by dt, which is going to be y to the power of 4 plus 2x y squared y primed dt. Okay, so what is that? That's going to be equal to 0. I'm not going to go through all of the details, but that's equal to 0 based on the fact that we know that x1 and x0 are both equal to 0. So here we're just left with minus the integral of y to the power of 4 dt. That's good. Plus twice the integral of twice xy squared, minus y primed dt. In fact, I can go so far as to bring the 2 out of the integral. Now notice that this expression here is the same as this expression here. So this is quite a useful little trick to bear in mind. Okay, that you might see this, for example, if you were to try to integrate, for example, e to the power of x cos x dx. Use integration by parts with this. Use integration by parts twice, and you seem to get back to this. But you can, what you can do is you can effectively add this to both sides, and it works out in the end. Okay, you haven't quite gone in a circle, in a full circle. So what we can do here is, if I just think of I as this thing here, then I've got minus the integral of y to the power of 4 dt minus 2i. So that means that 3i is going to be equal to minus the integral y to the power of 4 dt, and therefore I is going to be equal to a third the integral of y to the power of 4 dt. Minus a third, sorry. Minus a third the integral of y to the power of 4 dt. Yeah, so far so good. So that's that bit done. Okay, we've done that bit. And it's equal to, that was I, by the way. And we've figured that out there. So now we've just got this bit to figure out, the xy primed. And again, integration by parts. This is why you've got to stay organized, because there's integration by parts flying off all over the place here. And you've just got to decide how you're going to do this, which order you're going to do things in, and how you're going to bring all of that information back together. So, okay, what shall I call this? I'll call it, if I call this I, I'll call this J, naturally enough. So J, which is the integral from 0 to 1 of xy primed dt. U is equal to x dv by dt is equal to y primed. Du by dt is equal to x primed, which of course is equal to y, and v is equal to y. Now this is looking good. This is looking good because we've got the y to the power of 4 that we need. It looks like we're going to get the y squared here. So u times v, xy, between 0 and 1, that's going to be 0, minus the integral from 0 to 1, v du by dt, y squared dt. Bingo. Which is going to be, that's going to be 0, minus the integral from 0 to 1 of y squared dt. So in other words, this thing here, which is I plus j, it gives me minus a third the integral from 0 to 1, and I forgot my limits in here, naughty, y to the power of 4 dt, minus j. Now j is equal to minus this, so it's going to be plus the integral from 0 to 1 of y squared dt. Rearrange, that's equal to 0. Rearrange this, you get the integral from 0 to 1 of y squared dt is going to be equal to a third integral from 0 to 1 y to the 4th dt. Okay, a lot of integration by parts. I personally haven't seen a way to avoid that. If you don't like the solution that I've presented here, find your own solution. Find a better solution. And I don't mean that in a sarcastic sort of way. This is how problem solving works. This is how you develop in your problem solving skills in mathematics. If you don't like a solution to a problem, investigate. Try to find a better solution. So it's not me throwing out some sarcastic challenge to you or something like that. I mean it. If you think there's a better solution, go ahead and try and find one. I'm all ears. This is my solution that I came up with. This is the solution that if I was doing this paper, that I probably would have submitted. Okay, but yeah, try to find a better solution if you think that one exists. Okay, so on to the last part then. And for this last part, it's kind of a similar appearing result that we're after, but we're given very little information about how to derive the results. We're not given anywhere near as much information as we were given for this one. But as is usually the case with a step paper, if you're given hints for the previous parts of the problem, and then for the last part you're not given a hint, probably you need to do something that's kind of similar, although not exactly the same necessarily. It will just be some kind of simple adaptation, usually quite simple, to the technique that you've used in the first few parts to arrive at a result in the last part. I say a simple adaptation. Simple when you see it, but if you don't see it, it's not so simple. Okay, so let's get going. What do we need to do? By the way, guys, I'd be really grateful if you would hit the subscribe button for this channel. At the time of making this video, I've only got a few subscribers on this channel, but I really want to grow my audience. I want to get these videos to people that need them. Really want to help people prepare for their STEP and MAT exams in particular, but also A-level maths, further maths, and GCSE and IGCSE higher exams. So if you do know anybody that will benefit from these videos, please let them know. Hit the like button, and if there's anything that you want clarified, if there's anything that I've not really explained too clearly, please leave a comment in the comments section and I'll get back to you, because I record these videos with as little editing as possible. So that means that there's no script here when I record these videos. How things come out is how they come out, and that's how they go into the video. That's how they get uploaded. I try not to edit things out. First of all, because I'm too lazy to do it, but second of all, this is part again of the problem solving process. I'm trying to communicate my thoughts to you in a suitable way, and sometimes those thoughts are not necessarily completely they're not completely clear. So I can only, when I say something, I'm trying to express certain ideas, but it's off the cuff as it's coming out. So if there is anything that you really would like to know more about what I've said, that maybe I've misspoken, or maybe I've said something that's not quite so clear as it could be, ask for clarification in the comments section. Okay, so let's carry on with this problem. So the next part, and the final part, is we need to prove that, I don't think we're going to need this again. I'm going to leave it there. I don't think we actually need this result again. We need to prove now that the integral from 0 to 1 of y primed t squared dt is equal to the integral from 0 to 1 of y of t squared dt. Okay, so all it says is prove also the relation this. No indication given about how we're to do this, whether we're to use integration by parts, integration by substitution, or any other technique. It turns out that it's not too dissimilar to what we've already done. It actually turned out to be a little bit more straightforward. So having said that, I can't quite remember what I did. So I've got my notes here. So the first thing that I tried, and it is about just trying things out. So let's go back to our differential equation that we're trying to solve. So it's y squared minus 1 y prime plus y equals 0. The first thing that I tried, because I noticed the y primed t squared here, I thought, okay, in the previous part we multiplied through by x. Maybe in this case I can multiply through by y primed. Why y primed? Because of the y primed squared here. That's going to give me a y primed squared here. You could argue, well, what about the y squared here? Couldn't you multiply through by y? We'll come back to that in a second. But first, I tried y primed. So we get y primed, y prime prime plus y squared minus 1, y primed squared plus y times y primed equals 0. So I had a little bit of a play around with this, and I'm not going to write up all of the details, but I didn't really get anywhere with this. Okay, so remember, with these videos, I'm really wanting to communicate sometimes the mistakes that I've made with my solutions to these problems, even if sometimes those mistakes are quite naive. In retrospect, I might look back and I might think that was a really silly thing to do. It's not really a silly thing to do. It's just how it works sometimes. You don't necessarily see the wood for the trees. And by the way, I've got another question coming up, another video that I'm going to make on another question from this paper, from the 1990 Step 2 paper, where I really didn't see the wood for the trees. Okay, I made a right old mess of one of the problems. I'm gonna do another video on that one at some point. But watch out for that one. So this didn't work. Okay, I tried the integration by parts. I'm not going to write out all of the details, but it didn't work. Okay, didn't want to do that. So then I tried something else, which I'm just looking at my notes now. So I've got a little bit lost with my notes. What did I try? Okay. So actually, first of all, I just started with this. I did bring this into play at some point. Okay, but not straight away. Somehow I hit on the idea of just actually trying to integrate y primed squared dt. And guess what? This is another integration by parts. Okay, so u equals y primed, dv by dt is also y primed, du by dt is y primed, and v is going to be y. So what we get here is u times v, y primed between 0 and 1, minus the integral from 0 to 1 of y times y primed dt. And okay, that's going to be equal to 0. So this is just equal to minus what the integral from 0 to 1 of y prime dt. And it was this that gave me the idea of what I needed to do, okay, going forward. Or one thing that I could do. And this is how it works sometimes when you're trying to solve a problem. This is why it's so important that sometimes you just go along with your ideas, because the idea that you have may itself not work, but it may indicate something else to you which is going to work. Or even though in your head you might have had an idea and you were only able to take it so far in your head, once you've got it on the page and you can see things much more clearly, it's easier for you to see where to go from that point forward. So in my head, probably, I don't know, I didn't see the whole solution kind of set out before me in my head. I probably only saw it up to this point, kind of vaguely. I probably didn't even have this exact thing in mind. It was just kind of some vague, nebulous kind of idea that I had about what I was going to arrive at. But actually putting it down on the page, and now I can see where things need to go much more clearly, because I don't want to deal with that, but because here I multiply through by y prime, this suggests that maybe if I multiply this through by y, I might make a bit more progress. So I get y, so that's going to be y cubed minus y times y primed plus y squared equals 0. Because now if I rearrange this, I get y cubed minus y primed plus y squared equals minus y times y primed. And now if I integrate through between 0 and 1 with respect to t, remember we are integrating with respect to t, y cubed minus y times y primed dt plus the integral from 0 to 1 of y squared dt equals the integral from 0 to 1 of minus y times y primed dt. That minus sign can go on the outside here. Okay. Things are starting to look promising now, because this over here is just equal to, remember we've got the minus sign here, that's fine, the integral from 0 to 1 of y primed squared, or y primed of t squared dt. We've got the integral from 0 to 1 of y of t squared. The only thing that I've got to worry about now is this thing here. So we've got the integral of y cubed minus y primed dt from 0 to 1. Well, this is just equal to the integral from y of 0 to y of 1 of y cubed minus y dy. Again, kind of integration by substitution kind of idea. Well, this is easy, right? This is the kind of integration that you do right at the beginning of your A-level maths course. So leaving out of the specific details, this is going to be equal to 0. There we go. Okay, 0 plus integral of y of t squared dt is equal to y primes t squared dt between 0 and 1. So get rid of the 0. We've done. Okay, and that's the solution to not only the final part of the problem, but the whole problem. So that's question 8, problem number 8 from the 1990 sixth term examination paper. I know it's taken a while to get through the solution, but that's how it is sometimes. If there is anything that you want to ask, anything that you need clarification on, please leave a comment in the comments section. I hope you found this video useful. I'll be uploading plenty more videos over the coming weeks and months on sixth term examination papers and mathematics admissions tests, as well as other problems from other sources that I can find. Any interesting problems. If you've got any ideas, by the way, let me know. If there's any problems that you'd like me to go through. But that brings us to the end of this problem and the end of this video. Thanks for watching, guys.